Okay, so semiconductor diodes are actually main function because our whole, from the previous subtopic, we know that the whole entire country's transmission electricity is actually using alternating current. But we don't, like for example, our laptops or our computer that's in front of you right now, the screen in front of you right now, it's on all the time. It being that it's on all the time, it means that it is actually supplied by direct current. Okay, but our electricity, all right, in the subtopic of transformer and also transmission of electricity, that the whole entire electrical um transmission throughout the whole country is actually using alternating current. So we need to convert from alternating current, all right, to direct current, all right. The alternating current must be converted to the direct current. So in order to convert alternating current to direct current, we need to use one thing called semiconductor diode, or diode in short. Okay, diode is actually the component that you have learned before previously in RBT. All right, RBT you've learned before diode. Another name of diode that you would understand better is known as the LED. All right, the LED that when electricity goes through, there's a flag looking thing inside the glass, and then it actually lights up when electricity passes through. That is actually a diode. Okay, so before we go into the functions of the semiconductor diode as what your textbook is actually showing, I think it's more important that you understand what semiconductor is and how was diode being produced out. Okay, so over here, I'm going to jump to the notes that I've sent to you previously inside the WhatsApp group. Okay, so let's talk about metal and insulators. Metals and insulators are something that you are used to hear previously. All right. Hey, I just noticed one thing. I talked so long already. No one tell me that I'm not sharing screen. Man, how come? So you all pakai listen to what I say only lah just now. Okay, so I hope that you guys are seeing my screen right now finally. All right, so you have to understand what a semiconductor is. So first thing first, metal. Okay, we all know that metals are good conductor of electricity. Why they are good conductor of electricity? Because metals have a lot of free electrons. Free electrons that is easily to move between atoms. The electrons inside the metal, they can actually move around the atoms. All right, that's a special thing about electrons. Okay, so because they're good conductor of electricity, the resistance of metals are generally very low. How come this one keep on? Okay, so if their conductors are generally low, wait, sorry, a little bit disturbance because the Form 4 thinks that they're having class with me today. That's why I have a few Form 4 coming in and then going out again. Okay, now, okay, metals, because their resistance is very low, in terms of direct current, their current, the ability for current to flow is actually very high. Okay, so that's metal. But for insulators, we know that they are poor conductor of electricity. That's the reason why we call it insulators. So the main reason why they are poor conductor of electricity, because they have very few electrons to move around. When they have few electrons to move around, their resistance of the insulators is actually very, very high. All right, being that high resistance, when the resistance is high for insulators, the ability to allow current to flow is actually very low. Okay, so I noticed there's something wrong with my PowerPoint. Do give me a very quick moment to close this and then switch it on back again. Okay. Now, semiconductors. All right, we talk about metal and also insulators just now. So semiconductors is stuck in the middle. That's the reason why it has the word semi there. So for semiconductor, all right, it is a material with electroconductivity that is in between the conductor and the insulator. All right, it has the conductivity, which means that semiconductor resistance is between conductors and insulators as well. So pure semiconductors are silicon and also germanium. All right, silicons and germaniums are actually pure semiconductors. So at the special thing regarding semiconductors is that at 0 Kelvin means at the negative 273 degrees Celsius. All right, 0 Kelvin, the absolute temperature, is actually negative 273 degrees Celsius. All right, semiconductor behave like an insulator. Behaving like an insulator means it does not allow current to pass through. So when the temperatures start to increase, even if it's just negative 250 degrees Celsius, all right, the conductivity of the electricity increases because the resistance has been lowered. All right, as the temperature increases, the resistance starts to drop and therefore allowing current to increase. And when I talk about semiconductors here, I'm talking about direct current. All right, I'm talking about direct current. So you would notice previously, even in term ionic emission, we were talking about direct currents as well. Okay, so when we talk about resistance being lowered, current increases, we are talking about direct current. Okay, so next we are going to talk about charge carrier. So because I want to write properly, all right, let's talk about charge carrier. But before we talk about charge carrier, we talk about something basic that you have learned previously. Now, in an atom, all right, for an atom, we know that there is nucleus in the middle, nucleus which have protons and also neutrons. Okay, and we have electrons orbiting around them. Okay, so if an atom has additional electrons, all right, it receives additional electrons, all right, more electrons compared to protons. In chemistry, what do you call the atom, all right, when there's more electrons compared to the number of protons? Write the answer inside the chat box, please. What do you call the atom when the number of electrons is actually more than protons? Ada orang kat sana. Ion. What kind of ion? Yes, it's ion, but what kind of ion? When electrons is more than protons, anions, or more specific, negative ions. All right, negative ions. All right, then when we have proton number more than electrons, which means it has insufficient or less electron in the atom, we called it the positive ion, correct? Now, when we talk about physics electricity, okay, when the electrons is actually, when the number of electrons is actually more than the number of protons, we call it a negative charge. And when the number of protons is more than electrons or not enough electrons in the circuit, we call it a positive charge. Okay, so that's the difference between chemistry and physics, but it's actually still the same thing. It's just that we don't call it ions anymore, we call it a charge over here because we're talking about electricity. Okay, so in terms of electricity, last time what you understand about electricity is that the electrons flow. Electrons flow from positive to negative charge. Electrons will flow from negative terminal to the positive. But then current will flow from the positive to the negative. Now, let me just, due to the number of students in the class right now. All right, so let's just say I have a positive terminal and this is my negative terminal. Positive is the longer one, negative is the shorter one. So what happens usually is that the electrons, what you learned previously in RBT and in science, it is the electrons that flow from negative to positive, right, due to the attractive forces that is existing at the positive terminal. Then the current only will flow from positive to negative. And again, as you previously recall in chapter 3, current is actually the rate of charge flowing in the circuit. All right, so over here, students always have concept that it's the electron that's flowing in the circuit. But do take note, actually, in one term, all right, electron conductivity in semiconductors occurs because there are actually two types of charge carrier. All right, there are two types of charge carrier, which means there are two types of carriers that is allowing current to flow. All right, the first charge carrier is a negatively charged, and they are free electrons, the conventional electrons that we are talking about. And then the positive charge is actually holes, not protons, but holes. Okay, so what is holes actually? Okay, we will go to this. All right, the slides will actually tell us what are holes in a short while. Okay, so I'm going to explain what is a hole about through this slide and also the next slide. So the characteristic of a silicon atom, all right, because it's pure semiconductor, all right, silicons are pure semiconductors. So silicon has 4 electrons in the outermost shell, means that electron has 4 electron valence. Okay, silicon has 4 electron valence in the outermost shell, and they will share the 4 electrons with 4 neighboring silicon atoms to form 4 covalent bonds. All right, please do take note that what I'm explaining right now has been taken out from the current syllabus, but I think it's important for you guys to understand this before you go to the actual subtopic, which is actually semiconductor diode. This is how diode is being produced. Okay, so each covalent bond will have a pair of electrons, and every single atom shares 1 electron with each of its neighbors. So, like for example, this is the silicon atom right now, and the silicon atom has 4 electron valence that's at the side over here. So then we have another silicon that is actually sharing 4 other silicons that is sharing with the main one. See, there's one here, another one here, another electron here, another electron here. So there's 4 covalent bonds here. Okay, so over here, what happens is when silicon has 4 electron valence sharing with 4 different silicon atoms, there's no free electrons moving around. So when there's no free electrons moving around, there will be no electrons to conduct electricity. All right. So when there's no electrons to conduct electricity, that's the reason why it has high resistance. All right, high resistance because there's no free electrons. All right, and that is why pure silicon crystal is actually an insulator at very low temperature. But as the temperature increases, all right, as the temperature increases, the electrons will actually absorb the heat energy, all right, energy of the vibrating atoms will be absorbed and causes the electrons to break free from the atom, from the covalent bond. All right, here the breaking free is actually breaking free from the covalent bond. All right, breaking free from the covalent bond, not breaking free from the metal surface. Okay, for every electron that is broken free, there is a hole in the bonding structure between the atoms of the crystal. Later on, I will let you know what is a hole about. It's in the next slide. So some holes are said to be the carriers of positive charge, and one outer electron, Wei Heng, one outer electron from the neighboring atom will fill the hole at the same time will produce a hole at Y. So when the valence or the outer electron move to the left, the hole will move to the right. So this is the physical origin of the increase of electrical conductivity of the semiconductor with the temperature. Wei Heng's question is, so electric conductivity depends on the temperature as well as the number of free electrons. Yes. All right. It does depends on the free electrons that is moving around. Okay, now what is holes? Okay, assuming let's just say we are playing moving around the chair. I have, let's say, 1, 2, 3, 4, 5, 6, 7, 8. All right, I have 8 chairs here. Okay, assuming that is a chair. So I'm just going to put a simple structure. Okay. Okay, now let's just say one thing. I have 1, 2, 3, 4, 5, 6, 7, 7 chairs right now. I'm giving you guys an analogy of electrons and also holes right now. Now there is 7 chairs set by 7 person on the chair. Okay, so what happens here is that if the rule of the game is actually that when you want to move around, you need to have an empty chair for you to move. So right now there is 7 chairs and there are 7 people sitting on it. So it's not possible for the students or the people to actually move around in the chair. But the minute I actually take a chair and place it in front of the person here, this chair number 1, now what happens here is in order to come to this chair, the person have to move to the one in front. Okay, so when they actually move to the one in front, wait, okay, so this will leave an empty chair. All right, this empty chair will actually allow the person on the right to move over to the second chair, and then the third person move to the third chair and move on like this. So what you can see is that, all right, the people is actually moving towards the left, while the empty chair, all right, the empty chair is actually moving towards the right hand side. Okay, so in this case, this is similar to electron. Okay, so in electron situation, let's just say back to here. All right, assuming the person is an electron, and you do notice that throughout the whole entire year, this year, I keep identifying students either as an atom or an electron because it's easier to explain and student can analyze better. Now, so over here, there's an empty spot here. Just now when I mentioned that pure semiconductors, all the electrons are actually fixed. All right, they have one silicon atom has 4 electron valence. All right, that 4 electron valence is shared by 4 other silicon atoms. So all the electrons are actually in a covalent bond. So at low temperature, the electrons are all in covalent bond, causing it to have high resistivity. All right, the high resistance in the silicon atom. So when the temperature increases, all right, when the temperature increases, one electrons will escape from the covalent bond and move towards the positive terminal. So if it moves towards the positive terminal, all right, that electrons would leave behind an empty space, and that empty space in semiconductor is what we call as a hole. All right, in semiconductor, that empty spot is called a hole, and hole are actually assumed to be a positive charge. Why? Because if you recall back what I mentioned just now, all right, if less electron in the atom is considered as a positive charge. Less electron in the atom. There are more number of protons compared to electrons in the atom is considered as a positive charge. So when the electrons actually absorb heat from the increasing temperature. The electrons will escape from the covalent bond and move towards the positive charge. All right, that's out of the view already. So they actually leave an empty hole back at its original position. So what happens here is the electrons from a neighboring covalent bond will jump and move towards that empty spot. And this will cause all the electrons to keep moving so that they actually fill up the empty spots in front. Why? Because the positive charge, the positive terminal of the battery is on the left. All right. So the electrons are negative charge. So they will keep being attracted by the positive charge, causing all the electrons to move towards the left while the hole move towards the right. Okay. So are you clear on what is holes right now? Are you okay with what is holes? Okay, all right, good. Now let's look. I should have just transferred everything into PowerPoint. At least it's easier for me to scribble around. Something's wrong with my PDF today. Used too much already. Okay, now, so over here, all right, so this is what happens. Initially at the covalent, there's electrons over here, okay, but this electron actually moved out when the temperature increases. All right, the electrons receive enough energy to break free from the covalent bond, leaving an empty space at its original position. So that empty space is actually what we called it as a hole. All right, then electrons from a neighboring atom, which is this one, it will actually jump to fill up that empty hole. So when it moves towards the left, the hole will move towards the right. So this is how free electrons or holes become a charge carrier. Okay, they allow the charge to move. Charge carrier means to allow the charges to move. Now, semiconductor, when it's being pure, it's very difficult for us to do much of the stuff, because as you notice nowadays in our electrical appliances, as the temperature increases, we have a demand for our electrical appliances to work at its optimal function as well. All right, so if the temperature continue on to rise, the resistance will actually continue on to drop for pure semiconductor, but that's not exactly what we want. We want to maintain the temperature so that our electrical device does not get spoiled. All right, so that is the reason where they need to, not they need to lah, all right, because they were the one who created it last time, the physicists and the scientists. All right, so they have to dope the semiconductor. Now, doping is a process of adding a certain amount of specific impurities, all right, which means instead of pure semiconductor in the structure, they add other materials inside there, other chemical elements inside there. All right, we're not talking about liquid stuff. Chemical doesn't mean it's only liquid. Right, a certain amount of impurities called the dopant, all right, to a pure semiconductor to increase its electricity conductivity. So in order to increase the electricity conductivity, there are two types. Either you cause it to have more electrons, all right, either you have it to have more electrons, or you make it less electrons. When there's less electrons means there is more holes. All right, so if there is less electrons, there'll be more holes. If there's more electrons, there's more free electrons. All right, there's more free electrons flowing. Now, so the first thing is N-type semiconductor. N-type semiconductor comes from the word negative. All right, N-type semiconductor comes from the word negative type of semiconductor. In physics, when we say it's a negative type of semiconductor, it means that it has more electrons. Okay, why? Because you see, N-type of doping is to produce abundance of electron in the semiconductor. So the first slide that I was talking to you guys just now, when there's more electrons, it is a negative charge. All right. So if it's a semiconductor, more electrons means that it's a negative type of semiconductor. Okay, now silicon has 4 electron valence at the outermost the outermost orbit or the outermost shell. So each electron is covalently bonded with one of the 4 adjacent silicon atoms. So how do we want to make sure that it has more electrons? Okay, in order for it to have more electrons, we add an impurity. All right, we add an impurity, for example, phosphorus atom that has 5 electron valence. Okay, because silicon has 4 electron valence, all right, 4 electron valence at its outermost shell. So when you add an impurity that has 5 electron valence, 4 of it will actually share. So you have a look over here. This is silicon. The one positive and white color are actually silicon atoms. The middle one is actually a phosphorus atom. Phosphorus atoms has 5 electron valence. So that's 1 covalent bond, 2 covalent bond with the silicon, 3 covalent bond with the silicon, and 5 covalent bond with the silicon. 4 covalent bond with the silicon. So the fifth one, which is over here, it's not bonded to any other structure. It's not bonded to any other phosphorus atom. So this electron now becomes a free electron, free to move throughout the whole structure. All right. So that this free electrons will be the one that increases the conductivity of the silicon. So in terms of its concept, all right, if an atom with 5 valence electron or pentavalent atom is doped into the pure semiconductor, dope means to add in. So then each of the pentavalent atoms have 4 covalent bonds and 1 extra electrons. So all we need is just a very small amount of quantity of impurities to create enough free electrons to allow electric current to flow through the silicon. All right, so it just need a little bit of amount, then you have a lot of free electrons moving around. So when we have a lot of free moving electrons, which means most of the charge carriers are free electrons. The one that conducts the electricity is the free electrons, and the holes are the minority carriers. Why the holes are minority carrier? Why holes still exist? Because, all right, when there's electricity, there will be resistance. When there is resistance, there will be heat. And this heat will be absorbed by the phosphorus atom and the silicon atom to release some of the electron. All right, some of the electrons will actually be able to absorb the heat energy to break free from the covalent bond. So when they break free from the covalent bond, they will join with the rest of the free electrons to move around. But remember, every single time an electron, all right, every single time an electron moves away from that empty spot, it leaves behind a hole. All right, so the hole will actually allow another electron to actually sit back at its original spot, and the original spot of the other electrons is another hole again. So holes are still existing, and it is the minority carrier. Okay, so since pentavalent atom donates an extra electron, therefore in physics we call them a donor atom. Okay, so an example of a pentavalent atom is phosphorus, arsenic, and antimony. All right, it's there's no harm for you guys to actually memorize a little bit more if you want to understand semiconductor. All right, when school reopens, I'm going to teach you guys, I'm going to analyze the whole trial papers with you guys already. There are already 15 sets of trial papers on hand already. All right, so let's go to okay, sorry, one more thing. Because there's more free electrons, that's why it is negative. All right, negative type of semiconductor. All right, in short, semicon. All right, so here this is how they get the N type of semiconductor. Okay, next is actually to go to P type of semiconductor. Me very quickly to just get this here. All right, so P type of semiconductor. Okay, P type of semiconductor, just now we learned about the N type of semiconductor. So now P type of semiconductor actually stands for positive. All right, positive type of semiconductor means there is less electron. Okay, so here what happens is that the P type of semiconductor or doping process is to create an abundance of holes. Not enough electrons, so it's abundance of holes. So how to create abundance of holes? All right, silicon has 4 electron valence again. We add in a trivalent, 3 valence electrons atom, all right, into the pure semiconductor. Silicon needs to have 4 electrons to actually merge, to form the covalent bond stably. All right, but when we add in, example, aluminium, which only has 3 electrons at the outermost orbit, so it only can form 3 covalent bonds, 1, 2, 3. So what happens is that the fourth layer is empty. When it's empty, that's a hole. If it's a hole, means not enough electrons and means that it's considered as a positive type of semiconductor. Okay, so when this hole happens, the electrons from another atom will move into the hole. When the electron move into the hole, it will leave an empty space at the back, which means it created another hole. All right, so this is the reason why, okay, atom with 3 valence electrons, when they are doped into the pure semiconductor, 1 electron is missing from the 4 covalent bonds. So the deficiency of the electrons are called holes. So when the current is passed through the p-type semiconductor, the hole is filled by an electron from another atom. All right. In this way, the hole moves from one atom to another. Okay. Holes here will be the majority charge carrier, whereby the free electrons are the minority charge carrier. Why free electrons are still minority? Same concept as what I mentioned just now. All right. When current passes through it, all right, there will be, when there's current, there is going to be resistance. And the resistance will cause heat. And the heat will actually be absorbed by the electrons and causing the electrons to break free from the covalent bond. All right, when they break free from the covalent bond, that electrons are the free electrons of the minority carriers. All right, so that's the reason why p-type semiconductors still have holes and it still have free electrons. Now, since trivalent atom accepts, all right, it will accept an electron, so they are called the acceptor atom. All right, but normally they don't really ask this already lah. All right, so an example of trivalent atom is boron, aluminium, and gallium that they normally use in semiconductor. All right, so this is a very important basic things that I think that it's important for you guys to understand. Okay, so far, are you guys all right? Okay. All right, good. Okay, so let's have a quick summary. P-type semiconductor, all right, pure semiconductor is either a silicon or a germanium. So dopant for N-type is actually a pentavalent atom. Penta means 5 electron valence. Okay, then it will create, because penta, it has 5, which means 1 additional free electrons. So its main purpose is to create abundance of electrons in a semiconductor. And the majority charge carrier will be free electrons, while the minority will be holes. Okay, so that's for N type of semiconductor. P-type semiconductor, for me, P-type is positive type of semiconductor. So positive type semiconductor uses trivalent atom, which has 3 electron valence in the atom. Example, boron, aluminium, and gallium. Its main purpose is to create an abundance of holes. All right, when it's abundant of holes, the majority charge carrier are holes, while the minority are known as free electrons. All right, so this is a comparison between the N-type and P-type. So for the rest of you who is still blur on this, please make sure that you have the PowerPoints that I sent out previously inside the WhatsApp group already, yeah? Okay, now let's talk about semiconductor diodes. Semiconductor diodes are what you are supposed to learn in your syllabus right now. So they skip all those basic stuff already. Okay, so let's see what else. Okay, so you have the forward semiconductor diode that is forward and reverse. So I'm gonna again tell you guys some basic stuff in the semiconductor diodes first. All right, so the basic stuff that you guys need to know is that semiconductor diode, it's a device, all right? It's the most simplest device in semiconductor, all right? It's made by joining a p-type and an n-type semiconductor together. That's the reason why I wanted to teach you guys what is n-type and what is p-type first, okay? So a diode is actually to join a p-type semiconductor and an n-type semiconductor next to each other. And this device allows current to flow in one direction only, but it will block the opposite direction. Now, so for me, how do I identify the semiconductor diode symbol? Okay, my key for you guys is that it's very important to understand this if you plan to understand about transistor. My key to you is that the arrow always, always points to negative. Okay, why? Let's just say example, we have a battery, positive and negative. Current will always flow from positive terminal towards the negative terminal at the external circuit. All right, the current will always point towards the negative terminal. Now, a semiconductor diode has an arrow and then a straight line. So how do I identify which is which? Okay, my key is the arrow always points towards the negative. So this looks like an arrow and it's pointing towards this vertical straight line. So this vertical straight line is actually the N type of the semiconductor, while the arrow is actually the P type semiconductor or the positive type of semiconductor. So in other words to say, the connection here is P, this is N. All right, I hope this one helps you guys to clarify how to identify p-type semiconductor and n-type of semiconductor. Okay, so are you guys clear with this? All right, switching slides in 5, 4, 3, 2, 1. Okay, now, so the PN junction, what is a PN junction? When they took a p-type semiconductor and an n-type sticking next to each other, this middle part here is known as the PN junction. All right, so the PN junction is formed when an n-type and p-type semiconductor join together. The boundary is called a junction, and it's very important for you to understand regarding this junction. I just noticed one thing. I've been talking without my mic on and no one tell me again. Hello from 5. Are you even inside the Google Meet?
Yes, teacher. Sorry, teacher. I didn't know you were a mute. I thought it was like my earphones going broken.
Next time please voice out. I seldom have this kind of thing. Okay, what was the last thing that you guys heard?
The PN junction.
This part, did you understand?
Yes.
Okay.
Thank you, teacher. Sorry, teacher.
Next time, please let me know. Next time only left today and also Wednesday. Okay. All right. So a PN junction, the word junction is actually formed when the boundary, You see, yeah, I sudah kelang kabut myself. Now, the junction is actually the boundary between the p-type and the n-type region. Okay, so that is actually called junction, which means this line. Now, it's very important for you to understand regarding this junction line is because at the p-n junction, electrons from the n side needs to move to the p side to recombine with the holes. All right, it will actually jump from the electrons from the n side because n-type got a lot of free electrons. P-type not enough free electrons. So the electrons will actually jump over the junction to come over towards the p-type to enter the holes. All right. And then when it moves towards the left, what remains here is become the holes. So that's why it says that the electrons from the n-type will move towards the p side and the holes from P will actually move towards the n-type of semiconductor. So at the end of time, the n side will have more, it will be more positively charged, and the p side would be negatively charged when they are placed next to each other. All right, so that is a p-n junction. Now, why is it so important for us to understand that? Because, all right, if it's sticking next to each other, it wouldn't be a problem. The problem is if there is no electrons in the middle, right? The region around the junction, right, when that happens, will leave with no holes nor electrons. In this area here, they are already neutral, all right? Neutral, whereby most of the holes move away, all right? Most of the holes are moving towards this corner, and all the electrons are moving all towards the other side. No electrons is jumping through the junction. When no electrons jump through the junction, it becomes a depletion layer, a neutral region when there's no charge carriers, which means in the middle here, the atoms are still there. All right, the atoms are still there. It's just that there are no charge carrier. There's no free electrons. There's no holes. All right, so this depletion layer has no charge carrier, is a poor conductor of electricity. Now, it's very important because we are going to go into forward bias and reverse bias. Last time in RBT, when you learned regarding this, you learned that you have to put the flag, all right, inside the RBT. When you learn RBT, there's one part that looks like a flag, and the other part looks like the opposite direction. So the RBT teachers will always tell you, make sure the flag is connected to positive and the other side connected to negative terminal. All right. If you put it opposite direction, the LED will not light up. Why? Because of the forward bias and reverse bias. Okay. The ability for the LED or the diode to allow current to flow. That is known as forward bias and reverse bias in physics. Now, what you learned in RBT was very basic stuff. What we're learning right now is what happened inside that diode. All right, so we're going to learn about forward bias. Forward bias here, okay? Number one, identify the picture first, okay? Forward bias, I'm going to write this first. Forward bias is when the p-type, all right, the p-type of semiconductor, which majority are holes, so I'm just going to draw 4 holes here, and the n-type, I'm going to draw electrons here. Simple circuit. Now, how do I know it's a forward bias? Simple. For the battery, this is battery. The longer one is positive, the shorter one is negative. Forward bias is when the p-type is connected to the positive terminal and the n-type is connected to the negative terminal. Remember, P stands for positive. P-type means positive type of semiconductor. N-type stands for negative type of semiconductor. So forward bias means P-type semiconductor connected to the positive terminal of the battery. N-type semiconductors connected to the negative side of the semiconductor. Now, this is in terms of me drawing this circuit. There's another circuit that they usually use. Is this. All right. So how do we identify whether is it a positive or a negative? All right, very simple. The long one at the battery, long one is positive, shorter one is negative. Current will flow from positive terminal towards the negative terminal. All right. So if the direction of the current is the same direction as the diode, then the current can flow. So this is actually forward bias. Okay, current direction same as the diode direction, it's called forward bias. So what happened inside this forward bias? Okay, the P type of diode is connected to the positive terminal and the N type connected to the negative terminal of the battery. So okay, I noticed they didn't really say much about here, so I'm going to go back to my own drawing and use my own explanation for you guys. Now, when you connect this, current will flow, okay? Current will actually flow in the circuit, but you guys remember current flow because of charge flowing. So let's talk about the electrons first from the negative terminal. Electrons at the negative terminal of the battery will move as it is attracted towards the positive terminal. If it's connected to a PN semiconductor or a diode, okay, when the electron reaches the N-type semiconductor, electrons are negatively charged. I'm explaining in terms of things for you guys to understand better. Okay, the electrons will come in here and it will be very, very much attracted by the positive charge. So the electrons, what happened is that these electrons will have the ability to jump to the p-type. All right, the electrons will actually jump towards the p-type. When it jumps towards the p-type, what happens? The hole goes over to the n-type. But when it goes towards the n-type, the electrons from the negative terminal will still be able to move. Why is it all grouped up? All right, the electrons on the negative terminal will continue to enter, and then the holes will keep on moving as well. Okay, so when the holes keeps on moving, what happens that it will keep on being attracted and move towards the positive terminal, hence allowing current to flow. So the key thing is the electrons can jump through the junction. When the electrons are able to jump through the junction, then the current can flow. All right, let's look at what the textbook say regarding this. Okay, the textbook says that when a diode is forward biased, okay, when the diode is forward biased, holes will move towards the N-type of the semiconductor, while the electrons will move towards the P-type semiconductor. So the depletion layer becomes thinner, and the junction voltage across the depletion layer decreases, resistance becomes very small, the current passes through the diode, causing the light bulb to be on. All right. So they only say that the junction becomes thinner. All right. Holes move towards the N-type, while electrons will move towards the P-type. The depletion layer will become thinner because the electrons keep on moving. All right. Electrons will keep moving from the N-type to the P-type, and the holes move from the P to the N. All right. So when the junction becomes less, right, this junction become less, the resistance become very small, and the current will actually pass through. All right, this is forward bias. Now, in terms of reverse bias right now, okay, for reverse bias, what happens here is that forward bias P-type semiconductor is connected to the positive terminal of the semiconductor. Right now, it's the opposite. Reverse bias is when the positive terminal of the battery is connected to the N-type semiconductor, where there are electrons. And then the negative terminal of the battery is connected to the P-type semiconductor. Okay, a simpler version circuit is the arrow always pointing towards the negative. All right, this is the simpler version of the circuit of a reverse bias. So I'm going to analyze over here first. So when the current from positive will flow towards negative, but when the current reaches the diode, my current from the circuit is supposed to move towards the right hand side, but my diode arrow is pointing towards the left. So if it's one current pointing towards the right, but the diode is pointing at the same head-on direction, current cannot flow. All right, no current is able to pass through the diode. So if there's no current passing through the diode, if there's a light bulb here, this light bulb will be off. All right, the light bulb will not be switched on at all. So what happens in terms of the electrons and the junction? Now, p-types are holes. When it's connected to a positive and negative terminal is strongly attracted by the electrons. So the electrons from the negative terminal will move towards the p-type. And what happens here is that these holes will actually move. Let me try to do one thing first. All right, this holes, the electrons from the negative terminal of the battery will move out, okay, causing the p-type to be negatively charged. All right, the holes will actually be eventually keep on being filled up by the electrons. Okay, then what happens here is that these electrons at the n-type, okay, it instead of going towards the opposite direction, it is more strongly attracted by this positive terminal. So what happened is all these electrons from n-type will actually move towards the positive terminal. All right, it will keep on moving towards the positive terminal. When it keeps on moving towards the positive terminal, the junction here will become bigger and bigger. All right, there'll be more neutral region in the middle here. Why? Because the n-type is not crossing the boundary. The electrons from n-type is not crossing over to p-type. All right, there's no electrons jumping from the p-type to the n-type. Okay, so when this happens, the light bulb will be off. Okay, let's go back to the textbook again. Now, okay, because I want to highlight and I want to scribble everything. All right, in your textbook, it says that when a diode is in reverse bias, the holes and the electrons will both move away from the depletion layer. Remember just now when I was talking about the junction, I said that the electrons need to jump over that depletion layer, right? The electrons need to jump over the junction. If they don't jump over the junction, the depletion layer will occur. So the depletion layer will become thicker and thicker, causing the voltage to increase, all right? The junction value in the middle here to increase until it has the same potential difference as the battery. When it has the same potential difference as the battery, it has very high resistance as well. When the resistance is high, current is low. So the current will stop flowing and the bulb does not light up. So this is reverse bias. Okay? So up to here, reverse bias, are you guys okay?
Boleh lah.
Thank you, Damia. Okay, now we're going to look into how semiconductor is being used. Now, semiconductor is very obvious in our everyday life. Why? Semiconductor is actually here. Our power supply, all right, even if, all right, this particular, all right, charger head, the multi-charger that I have, there are semiconductors inside here. Okay, so when there are semiconductors inside here, and do note that the semiconductor is getting smaller and smaller, lighter and lighter. All right, so why is semiconductor important? Is because the power supply, all right, this cables, all right, this this tree, I've forgotten what this is called already. All right, it is connected to the alternating current power supply that is transmitted from TNB. All right, TNB provide us with alternating current because it's cheaper that way. But we don't want to look and charge your handphone. Imagine if you're charging your handphone with alternating current. Alternating current means like this, the handphone is being charged and slowly switch off. It switches off for some time and then it start charging again. And then switch off again. And then charge again and then switch off again. I'm sure you don't want that. And then you imagine if that is your laptop that you guys are actually using right now in order to listen to my lesson. The laptop switches on and then starts shutting down. And then it's off for quite some time and then it switch on again. And then it shut down again. And then switch on again and then shut down again. That is how alternating current behave. Okay, but that's not what we have right now. We have our power supply always on. All right, our power supply is always there. Why? Because it's direct current. All right, TNB supplies us alternating current, but what we are using is direct current. So how to convert alternating current to direct current? That is what we know as rectification. Okay, so we're going to learn about rectification. There's two types of rectification. All right, the process of converting alternating current into direct current is known as rectification. And there are two types of rectification: half-wave rectification and full-wave rectification. Okay, so this is a full-wave rectification because there are 4 diodes here. All right, so I'm going to teach you guys how to draw a half wave and a full wave rectification. So I would strongly suggest to you guys, time to get paper and pen. All right. So I'm going to let you guys have a quick, go and grab paper and pen because you really need to draw this out. And from the analysis that I saw from other state trial papers, right, they came out this question, although our Selangor didn't come out rectification question. All right, other states did have rectification questions, so better learn how to draw. Now, this is still in your textbook. A half-wave rectification, all right, how does it happen? So a complete cycle of alternating current consists of 2 halves, the positive half and then the negative half. All right, so this is what I meant just now. Charging, discharging, charging, and then discharging, or switch on and then off. And then for some time, and then it switch on again and then off again. All right, so this is alternating current. Now, during the positive cycle, the semiconductor diode is a forward bias that allows current to flow through it. During the negative cycle, the semiconductor is in reverse bias, hence no current flowing. So this cycle of rectification is called half-wave rectification. So they vary the how say, as usual, textbook don't tell everything but expect you to learn everything. Now, so I'm going to teach you guys how to draw half-wave rectification right now. So on the left-hand side, put 2 dots. This is where our input is going to be. And our input is actually coming from TNB and it's actually alternating current. Okay, then you draw a simple circuit with a diode. Okay, and then passes to, this is going to be the output. All right, that is going to be our output. Okay, now what is going to be at output? Output can have a resistor. Output can have a light bulb. Output can be our laptop. Or in short, sometimes they actually use the word load, beban. Okay, and output can also be any electrical appliances. Whatever you can think of that is connected to the output. Now, how does a half-wave rectification work? So this is half-wave. I need to remind myself that this is a half-wave. Okay, so let's start. What other color is obvious? Okay, Hopefully that's obvious enough. Okay, when the top part is positive, when this is positive part, when the top part is positive, down here is negative, current will flow from the positive terminal towards here. All right. This current flow direction is same direction as the diode. So current can flow through. This part, the diode act as a forward bias. Current will be able to flow through, passing through the resistor, going back to the negative terminal. When it gets back to the negative terminal, the wave will appear at the output. Okay, the wave will appear at the output. When the bottom half, which is the negative half of the alternating current appears, which means the bottom part positive, the top part negative, it switched the terminal already. Okay, so current will start to flow from the positive terminal, all right, passing through the output. But in order for me to draw down here, my arrow need to reach the negative terminal, which is over at this side. But when I reach the diode, notice that the current arrow and the diode arrow is head on right now. So which means that when the bottom part is positive, my current, when it reaches the diode, it becomes a reverse bias. When it comes a reverse bias, it will not come out in the output. Why? Because current cannot flow through the negative terminal already. Okay? So when it doesn't flow to a negative terminal, then it flips to the top half again. So the blue one will flow passing through the diode, forward bias, and then back to the negative terminal. Then only it will appear again. Okay? Then when the negative half appear, positive flowing through the diode, reverse bias, the output, nothing appear. Okay? So it alternates, positive and negative alternates, but because of the forward bias and the reverse bias, only half of the wave actually appear. So that's the reason why it's called a half wave rectification. Okay, are you guys clear with this?
Yes,
Yes,
teacher.
Yeah.
teacher.
Good. All right. So if you're clear with it, then we're gonna go to something more challenging: full wave rectification. Half wave uses one diode, but full wave rectification uses 4 diodes. Okay, so let's go again to the textbook first. The arrangement, all right, according to full wave rectification, the arrangement of the 4 diodes are called a bridge rectifier. So I'm going to teach you guys how to draw this full wave rectification circuit. Okay, but let's see apa benda dia nak cakap. Okay, so which means a full wave rectification in terms of definition, a process where both half of the cycle of the alternating current is made to flow in the same direction. So the input is it looks like a sinusoidal graph, isn't it? All right. So the positive and the negative half from the input all becomes positive. It fully flips the wave from the negative to the positive, causing all the wave to appear there. So that's why it's called a full wave rectification. All right. So the most important part for full wave rectification is how to draw this circuit. All right. So I'm going to teach you guys how to draw this right now, but just give me one quick minute to just drink some water. Okay, so I hope you guys are ready. I'm going to teach you guys how to draw a full wave rectification. Now I'm going to draw 2 to 3 rounds. The first round you guys observe. The second round and the third round you try to learn how to draw. Okay, so first round, drawing a full wave rectification, observe first. Okay, um, why I'm teaching you guys how to draw a full wave rectification is mainly because last time they used to ask the student to draw out themselves. But nowadays, I noticed that they just leave the empty diode area. But in case they suddenly come out the old question again, then no harm learning, right? Okay, so I'm going to start drawing the full wave rectification. Let's start. Anyway, I do enjoy drawing it. Okay, so we're going to start with the input on the left. Input and output can switch direction. All right, but how do we know whether input or output? Is because the input has the power supply. All right, input has the power supply. So what I'm going to do is I'm just going to draw 2 dots over here. Okay, so these 2 dots, I'm going to draw a straight line vertically up, horizontally, and then vertically down again, like the hangman. And then after that, I'm going to go vertically down, horizontally, and going back up as though that it is in line with the top one. So this is actually the input circuit. Then after that, I'm going to use another color. I'm going to draw the output circuit right now. So how I'm going to draw the output circuit, I'm going to put the output at this side. This is output. All right, 2 dots. So I'm drawing it vertically down. Somewhere in the middle of this. All right, it's supposed to be a straight line, but I can't really draw that straight freehand. So again, almost in line here. I draw a horizontal line, vertical. But over here, I'm going to put a little jump in my diagram. This jump means that my purple color line does not touch the black color line, which means is like this. It's 2 different lines. All right, a black wire and a red wire. It's not connected. Okay, so that's the meaning of the jump. And then it goes all the way back to here, the terminal again. So over here, this is where we're going to put the diode. Okay, so I'm going to draw a bridge kind of thingy right now. As though that I used to call it looks like a diamond shape. All right, okay, so there's empty spots over here. Okay, so I'm done with the circuit. I'm going to draw the diode right now. The key for the drawing of the diode, all right, what is the key to draw the diode? All 4 diodes must point toward the same direction. Okay, and the parallel diodes also towards same direction. So that's my key to you guys. So what does it mean? Okay, it means that if you're going to draw it pointing towards the right-hand side, this direction, then all 4 of the diodes must look as though either diagonally towards the right. Okay, so example, if I'm going to show that all points towards the right, I'm going to draw the diodes like this. All right, the arrow points like this. Okay. All right, these 2 are actually parallel to each other. So you see, they are pointing towards the same direction. And I said all direction must point towards the right. So this is diagonally towards the right. So the other one points this way also, towards the right also. All right, so this is how I draw a full wave rectification, a full wave rectifier circuit. So I'm gonna add a resistor over here. Main reason, normally this is alternating current. Alternating current is high power supply. So you put a resistor over there to lower down the potential difference and the current flowing in the circuit. Okay, so this is how we draw a full wave rectification. So I'm going to teach you guys how to draw right now. So it's time for you to take up your pen and start drawing together with me. Okay, so we're going to start with the input. All right, so draw 2 dots for the input vertically above and below each other. Okay, then we're going to draw something that looks like a hangman. And then same thing for the other side, but opposite. Make sure these 2 arrows are actually in line with each other. So I'm going to draw it a little bit closer to each other. Okay, so that's going to be the first one. Now I'm using another color so that you can understand it better. Okay, so we're going to draw the output right now. So again, 2 dots. Okay, 1 going in the middle, like this. All right, horizontal like this, because we know that here is going to be the diamond, the bridge over here. And then almost in line with this. And then it has to jump a little bit so that it means that it's not touching the black color input circuit. And then you directly put a resistor to lower down the power supply. Okay, so remember, I'm going to teach you guys 3 times. All right, so I hope you guys are okay. Now we're going to go into the diode location. So diode location, draw the line. Try not to leave too big space, or else it's going to be very difficult for you to draw the diode. That's what I noticed. Okay. All right, then we're going to draw the diode. Now, you can actually point the diode towards the left, no problem at all. All right, but my habit is always towards the right. Okay, and I find it easy to draw the 2 parallel line first, then only draw the arrow. It's really, really easier. Okay, so we have a full wave rectification circuit right now. I hope you guys can draw that. All right, so do you guys need me to draw the 3rd round? Or is it sufficient already for you guys?
Boleh kot. Boleh kot. Cuba. Yeah, can.
And already, yeah. Good. All right, so please do remember how to draw a full wave rectification. All right, so I'm going to explain the concept. All right, I'm going to explain the concept for how does a full wave rectification starts from. Because the 2 circuits is the same, all right, I'm going to use it to explain it separately right now. Okay, so again, the input power supply is actually an alternating current power supply. Okay, shouldn't draw until so big. Input power supply is alternating current. Okay, so I'm talking about here positive, here negative. So I'm labeling the diodes D1, D2, D3, D4. Okay, and then every single time I'm done drawing, all right, the complete circuit, then I'm going to draw the output. So right here, what happens right now is that I'm going to start drawing the direction of the current flow. And remember the key, the current from the positive must come back to the negative terminal before I can draw the wave at the output. Okay, I repeat, the current that comes out from the positive must enter back the negative terminal first before I can draw the output. Okay, even for half-wave rectification, just now also you notice that I started from the positive moving towards the negative, then only I draw the output. If it doesn't come back to the negative, I don't draw anything at the output there. Okay, so let's start right now. Okay, so current from the positive moving through the black color circuit, reaching to this first junction. Now, it can't go to D1 because it's of reverse bias, but it can flow through D2. All right, the current is in the same direction as diode number 2. So it will actually flow past D2 and then coming here. All right, when it comes here, it will go through the resistor and obviously to the output. But I'm not going to draw anything here first because remember what I mentioned just now, my current needs to come back to the negative. So it passes through the resistor from bottom to the top and then it reaches the purple color line. All right, goes through here, jump over because it doesn't touch lah. Okay, it's another wire. And it comes through this junction. Now, when the current comes through this junction, it can go to D1. All right, but if it goes to D1, you go to D2 and then it come back again to this position. So that's not what we want. We want to go back to the negative terminal. So it goes to D4. Passing through D4 reaches the junction. Obviously, it can go to D3, but that's not the point right now. The point is get back to the negative terminal. So as you notice, current can come back to the negative terminal. If it can come back to the negative terminal, which means this positive forms at the output. Okay, that positive forms at the output. So right now, I hope you guys are okay. I'm going to start drawing the negative side. So the negative side, I'm using green line. All right, the bottom part is negative, which means here now becomes positive terminal. The top becomes negative terminal. Okay, so the bottom positive. Now let's start with our current flow. Current flow from positive. This is our current. It reaches the junction. When it reaches this junction, it cannot go to number 4 because that's a reverse bias. The current direction and diode number 4 is reverse bias, but it can go to number 3. It's forward bias with diode 3. So go to here, cannot go D2 because reverse bias. So you notice that it's the same direction right now as the red color arrow. So it passed through the resistor. Okay. And then it goes back. If you notice the same line as just now. But now when it reaches this junction, it can go D1, it can go D4. Again, there's no point going D4 because D4 will go D3 and then you'll come back in the same place again. We want to go to the negative of the green color here. So it goes to D1, forward bias, reach the junction, and then it goes through the black color line, not the purple one. I should erase this or else you get confused. All right, and then back to the negative terminal. If it back to the negative terminal, which means that it can go through the output. And then because same direction as the red color line, the output wave is positive also. Okay, so again, when the red color is positive, the top part is positive, then it goes through this, the green color, the red color line, then here positive. And then when it's the other side positive again, and then it flips like that. So that's the reason why it's called a full wave rectification. Okay? Are you guys okay? Need me to explain again?
No need, teacher.
Processing. Wait, cannot hear anything. Tungzhen, you said something. Need to explain again. Okay ka? Wei Heng, okay. The rest? Damia, are you okay?
Yes, teacher. Teacher, wait, again, is it the purple line first, right, teacher? Then the green one just now.
Okay, let's look at your textbook. Textbook easier. the textbook
Sorry,
one, because
teacher.
no, it's okay, don't worry. As long as you understand. Now, you see, let me snapshot this. The reason is I have been used to drawing the full wave rectification because last time textbook their full wave rectification very the not so complete. Okay, I cannot say not good. It's not so complete. So that's why I've always taught the rectification by drawing it myself. Okay, now for the positive cycle, which means the first part, okay, if this part is positive, current will flow. All right, when it reaches here, the current flows through D1. Even though this is almost it's different from what I draw, but the only difference is the output for this picture is actually at the bottom. My output is at the top. All right, there's the same thing only. Okay, so when the current flows through D1, passing through the resistor, okay, and then it goes back to the junction to D2, and then D2 will go back to the negative terminal. All right, this is the first part. So the resistor, the current actually flows in this situation from top down. For mine, the current flows from bottom up. Okay? Then when the negative part, the negative half, okay, okay. You know what? I'll just re-explain this part again. I see my picture. I think I scared later you will get confused instead. I'll re-explain this part. No worries. Don't worry about it. Okay. So when this top half, the positive half, this is positive on top. Let's just say this is terminal A, this is terminal B. Okay. So A is positive, B is negative. This is D1. Don't worry, Damia. This is D2. This is D3. This is D4. Now remember, just analyze what the circuit gives you. So the current will flow from positive. All right, this is our current flow. All right, reaching to this junction. D1 cannot go because of reverse bias, so it will actually flow to D2. All right, and then it will go through the resistor from the bottom up because this diagram is the one that you draw. All right, it will continue on flowing until it reaches this junction again. And then we want to get back to the negative terminal, so it actually passes D4 and then coming back out and entering back the negative part. So when it enters the negative part, the output will have the same positive as the top one. Okay, now that is when the positive, the first half cycle. When the second half cycle, the negative down here, which means terminal B now becomes positive. Terminal A becomes negative. Okay? When B becomes positive, current will start to flow, but in the opposite direction, if you notice right now. So when it reaches this junction, it cannot go D4 because it's a reverse bias. So it will go D3. All right? It will go to D3. And then if you notice, the direction now is the same as the previous current flow. All right? Going upwards, passing through the resistor from bottom up again. Okay? And then it goes back to the bridge. All right? And here, it can go to D4, but that's not what we want. We want to go back to the negative terminal. So it goes to D1. Okay? And then back to the negative terminal at A. So when it comes back to A, which means that current can come out from the output. But instead of the bottom part, all right, instead of the bottom part, because the current is flowing the same direction as the one before where A is positive, the wave actually gets flipped to the top. All right, it gets flipped to the top. So that's the reason why we have a full wave rectification where the blue and the green color one is actually being flipped to the top. All right, so this one is what we call a full wave rectification. Dami, are you okay?
Yes. Thank you, teacher.
Welcome. All right, but there's one problem right now with this power supply. Then you'll be saying, oh no, another problem. This power supply, just now when it's alternating current, okay, During alternating current, the input, okay, the alternate current is on and switch off. Then after some time only, it switch on again and then switch off again. Okay, now for a full wave rectification, you know how the power supply goes right now, you know? If you are if the laptop is directly connected to a full wave rectification, it will be switch on, switch off, switch on, switch off, switch on, switch off, switch on, switch off, switch on, switch off. All right. Why? Because it is increasing, decreasing, increasing, decreasing, increasing, decreasing. So we must do something to this circuit. Okay. Let's not look at this circuit anymore. Let's look at here. All right. In order to make sure it doesn't switch on and switch off, switch on and switch off back, we actually put a capacitor. All right. A capacitor parallel to the resistor, parallel to the load. All right. At the output there. Now, the main purpose of a capacitor is to charge, to store charges. What charges? The positive and the negative charge that we explained beginning of this lesson. All right, the capacitor will actually store the charges, the electrons and the holes inside there. So every single time when you are when you are charging, all right, when it's going up, the capacitor charges. But when the terminal switches, all right, when it switches terminal, the capacitor will discharge what was stored inside. All right, so instead of switching off, all right, the capacitor allows current to flow out to pass through the resistor. So instead of switch on and off, on and off, on and off, the capacitor actually allows you to keep your laptop on all the time. Okay, so that's the reason why nowadays when we look at our laptop, when we look at our TVs, right, it's always on. All right, you don't see it flicker. Why? The capacitor actually try to let this become a straight line instead. All right, the going downward part is not so obvious anymore. All right, so that is actually the function of the capacitor. Okay, so you see over here when the potential difference increases, okay, the capacitor will be charged and energy stored in the capacitor. Energy in terms of the charges lah. When the potential difference decreases, which means it's switching the terminal, the capacitor will discharge so that the output current does not fall to zero. So the energy stored in the capacitor will maintain the potential difference across the resistor, which means that when they switch charges over here, the capacitor will discharge and allow current to flow through the capacitor and the load. And it goes back to the capacitor also. All right. But when it charges up, the capacitor will actually store all the charges while it let current flow through here. Okay. A smoothened output wavefront shows the capacitor is functioning as a current smoother. So please do take note, the function of a capacitor is to smoothen the output waveforms. Okay, are you guys okay with this so far? This subtopic got no calculation, all conceptual. Okay.
Yes, okay.
Okay. Now, if you're okay until here, all right. Wait, let me stop presenting.